Good morning, guys. Now we are at the last part of our chapter on circular motion. Today we are gonna learn circular motion in non-inertial frame of reference. Until now, until now we assumed that our circular motion, our two-dimensional circular motion was in inertial frame of reference. In inertial frame of reference, that means the frame was either at rest or was at constant speed, was at constant velocity, no, not speed, constant velocity, and that's why we were able to apply Newton's law in each and every case of circular motion until now. But what about non-inertial frame of reference? In non-inertial frame of reference, velocity of frame is changing. That means frame is accelerating with some value of acceleration a, and we know that in non-inertial frame of reference, we cannot apply Newton's laws of motion. That is one of the limitation of Newton's laws of the motion. So what we did when we had to apply Newton's law in non-inertial frame of reference. Do you remember? Do you guys remember the person standing on a weighing scale in a lift? When the lift is when lift is at rest, weight of weight of human standing on weighing scale will be mg in inertial frame of reference. That means normally weight will be mg, but and apparent weight will be also mg, because lift is at rest. So for the person inside his frame of reference, the lift is at rest. So we can apply second law of Newton's second law of motion directly. We can apply second law of motion directly and find out his weight. So this apparent weight means what will the weighing scale show? So the weighing scale will show this much. Weighing scale will show this much weight, this much weight in Newton, or mass reading on scale, because the scale on the weighing scale shows us mass in kg. So what does the instruments in weighing scale do? They just WA by G. So here we will get M, which is actual mass of the person. What if the lift is either ascending or descending with constant velocity? If the lift is ascending or descending with constant velocity, that means for the person, his frame of reference will be inertial frame of reference. That means we can apply Newton's law without making any changes. So the calculation or reading on the weighing scale will be the same. But what if lift is ascending with constant acceleration A? That means, what I am asking, what if lift is ascending with constant acceleration A? You all have experienced when you are in elevator on lift. When lift starts to go upward, it starts to ascend, you feel heavy. After few seconds, you will not feel heavy, because when it starts to ascend, it has accelerated from zero velocity to some velocity, and from there, and that part of the motion will be accelerated part of the motion. Beyond that, lift will have some constant velocity, that means constant speed directed towards upward, so you won't feel heavy. But when it suddenly stops at your floor, you will feel heavy again. So what is happening? So what is happening? So in while studying laws of motion, we have already seen this. This is just revision to apply Newton's laws of motion in non-inertial frame of reference, accelerating with some acceleration A. What will we have to do? We have to apply equal and opposite amount of acceleration of frame to the object inside the frame. So if my lift is ascending with acceleration A, what will I do? I will apply same magnitude of acceleration A, but towards opposite direction. So if lift is going upward, my acceleration will be towards downward direction. So my effective acceleration will be my effective, and there is acceleration due to gravity acting on the person, even even if whatever may be the case, if it is, even if it is either it is a non-inertial frame or inertial frame, if this person is on the earth or any planet, there will be acceleration due to gravity. So effective acceleration on the person will be G plus A, because this is directing in same direction, so it will be G plus A. G plus A. So if so, what will be his apparent weight? So what will be his weight inside the this accelerating frame of reference? Excuse me. Now we have balanced our acceleration of frame of reference with acceleration on the object inside the frame. So now we can apply laws of motion. So weight will be mass into acceleration, that means G plus A. This will be in Newton. See here, when it was at rest, it was mg. Now it is m into G plus A. So effective acceleration has increased, and that's why this apparent weight has increased. That's why you will feel heavy while it is accelerating upward. What will be the reading of scale? Let's say scale. What will the reading shown on scale? It will be m into g plus a upon g kg. Because weighing scale is programmed for only divide by g. Because in normal case or general case, weighing scale is only designed to be used in non-inertial frame of reference. That means when frame of reference of weighing scale is at rest. So what will happen when lift is descending with constant acceleration? Lift is descending with constant acceleration. So if lift is descending with constant acceleration a, what will I do? I will apply same amount of acceleration but in opposite direction on the object inside the frame. So my effective acceleration will be g minus a. G minus a. So what will be my apparent weight? M into g minus a. Because of this minus a, we are able to apply Newton's law. That's why we can use this equation. So what will be the reading on reading on scale? M into g minus a upon g kg. That's why when lift is descending and it is accelerating, you feel light because now effective acceleration is less than acceleration due to gravity. Acceleration due to gravity. Now apply the same. Now let's apply same. Now let's apply same principle to the circular motion. Vertical circular motion in lift. Let's assume there is string tied to a weight and mass, and that particle or mass is performing the vertical circular motion inside a lift which is ascending with constant acceleration a. And the particle started his journey at bottommost position with velocity u, or velocity speed at the bottommost position is u. So what we will have to do? What we will have to do? If this is u and at topmost position, our velocity is v, and now and we know that t is equal to 0 here and t is equal to 6 mg here in inertial frame of reference. The analysis will be same. Just we will have to change value of g. Now we have to change value of g to the value of effective acceleration, because as a frame is accelerating towards upward, we will have to apply acceleration a on the particle in opposite direction, so that so that we can apply Newton's law and perform analysis, because in our analysis until now we have applied Newton's laws many times. We don't even realize that we are using Newton's law, but we are. The force balance, or when we just nonchalantly apply force is equal to mass into acceleration in case of tangential or centripetal force, we are using Newton's laws. So my effective acceleration will be g plus a, g plus a. Now I can perform, I can perform my analysis with using this g plus a. That means if I have to draw, if I have to draw free body diagram here, my this will be m g plus a. Weight of the particle will be g plus a. So at topmost position, to for particle to complete the loop, we know what is the limiting value to t is equal to 0. So, and what will be the weight? Mass into g plus a. So this m into g plus a, or m into effective acceleration, is providing necessary centripetal force for me. So if this is point A and this is point B, my mvb square upon r will be equal to m g plus a. So at point A, my vb will be root of will get cancelled, root of r into g plus a. In inertial frame of reference, my speed at topmost position was root of rg. Now it is root of r into g plus a. So we have accounted for the acceleration of frame of reference. Now I can apply conservation of mechanical energy between point A and point E, point A, B and E. So delta KE will be delta PE, and half of mu square minus half of mv square will be equal to m. Now here, rather than g, we will have to use a effective. That means g plus a into h. And what was our h? What is our h here? 2r. So if I put value of v, which is rg plus a here, I will get u is equal to root of 5 into g plus a r. If lift is going downward, my g effective will be g minus a. So my speed at topmost position will be root of r into g minus a, and here lift at downmost position will be root of 5r into g minus a. So I am just replacing g with a effective acceleration. You can also perform generalized vertical circular motion in non-inertial frame of reference. That means you can find the values of vertical displacement h, relation between v square and v and u, and force balance. That means relation between mass, tension, and centripetal force. H will be the same. H will stay same. H will stay same. If for generalize, H will be equal to R into 1 minus cos theta. Our V square was U square minus 2GH. But now I have replaced my G with G plus A. So my G will be replaced by effective acceleration into H. What will be the force balance equation? T minus M A effective into cos theta is equal to mv square upon r. So these are the generalized equation in VCM in non-inertial frame of reference. And effective acceleration is nothing but g bar plus magnitude of effective acceleration. A effective is magnitude of effective acceleration vector, and effective acceleration vector is just a second. Acceleration after accounting for acceleration of frame of reference. So if the question is asked regarding VCM in non-inertial frame of reference, you can solve, you will be able to perform any analysis and solve any question. We have seen many cases of VCM. You can perform any analysis if you understand the basics of non-inertial frame of reference. That is why I am always telling you to never forget the basics. To never forget the basics. So now let's take second case of vertical circular motion in VCM in non-inertial frame of reference. Now let's assume that VCM, a particle tied to a string is in a vertical circular motion and length of string is r, and this whole action is happening inside a trolley which is accelerating horizontally with uniform acceleration a. So what will you do? So what can you do? So what can you do? Let's take this particle, just forget the circular motion for a moment and just take trolley with acceleration a and this particle. So if particle as at the rest, what will be the only acceleration? If this trolley as at the rest, it will be only g. Now if we have to apply Newton's law on this particle, what will we have to do? Would we have to apply equal amount of acceleration in opposite direction? That's mean I will have to apply acceleration of magnitude a, but in negative towards negative x-axis, because my acceleration of frame is towards positive x-axis. Now these are vectors. And so for on particle now there are two accelerations which are acting at 90-degree. So if I use law of parallelogram and draw the diagonal, I will get effective acceleration. And what will be the value of this effective acceleration? A effective bar will be a bar plus g bar, but what will be the magnitude? It will be a square plus g square, because theta is 90-degree. So p square plus q square plus 2p cos theta, the last term will go 0 and I will only get this. So now let's come back to our circular motion. The effective acceleration, which is caused by acceleration due to gravity and frame of reference, is now at some angle phi with vertical. So my whole analysis will turn towards turn towards a vertical, towards a line in which is at angle phi with vertical. So initially my weight was at this direction, but now I will have to apply my weight in direction of A effective at phi. So if now Before my tension for completing the loop, tension in the string should have been greater than 0. My limiting value of tension was 0 at topmost position because here mass was, weight was acting directly downward. But what is happening? Now weight is gonna apply on this new axis which is at angle phi degree to the vertical. So now my uppermost point will shift here because this will be the point where the all of my effective weight is directly along the string towards the center m into a effective, and there is no force along this radius which is at angle phi, which is acting away from center to create the tension. So this will be my point of tension 0, and this will be my u. This will be my lowermost position point will shift to the left and uppermost position will shift to the right, because weight is gonna point towards the on this towards direction of a effective, which is inclined to the vertical at degree of phi. So at point B, now limiting case is tension is 0. So my minimum required centripetal force is provided by m into a effective. Now this m into a effective will be m into square root of g square plus a square. So my v will be r into square root of r into again square root of g square plus a square. If you are getting confused by two square roots, you can write it as r into square root of g square plus a square raised to 1 by 2. Once again, let's apply energy balance between point B and point A. Delta delta ke equal to delta pe. So half of m u square minus half of mu square minus half of m v square will equal to m. What will be my g effective? G square plus a square into h. Now my question is, what will be the h? What will be the h? Until now, we took h as vertical displacement. Vertical displacement. Why? Because our acceleration due to gravity was acting towards downward direction. That means my gravitational potential that means my gravitational potential was changing along vertical direction. But now effective acceleration due to gravity is along this new axis which is at angle phi with vertical. Always remember, in simple words, you are in the formula of potential energy mgh, your h, that means your height will be along the axis of g, will be along the axis of acceleration due to gravity. So if my acceleration due to gravity is pointing downwards, that means it is along vertical axis, then your displacement will be vertical in the equation of potential energy. But let's assume that if your g is along horizontal direction, then your h will be horizontal displacement. See, let me explain using work. What is work? It is dot product of force into displacement. Force into displacement. And this force is mass into acceleration. Mass into acceleration. So if I am applying acceleration in certain direction, change in velocity will also happen in certain direction, and s will also be in certain direction. So अगर velocity बढ़ रही है तो acceleration will be along the motion. That means displacement and acceleration एक ही direction में होंगे. अगर velocity कम हो रही है तो acceleration opposite होगा acceleration motion के. That means direction of displacement and acceleration will be opposite, but still they will be along same axis. हमने ये example देखे 1D मोशन में फोर्स है और कुछ तो डिस्प्लेसमेंट गया है. तो इन दिस केस व्हाट वी आर सीइंग फॉर वर्क if they are along the same direction, because what will be the work is actually scalar value, sorry, this will be fs cos theta cos 0 is 1, and if this is along the same direction, then if this it will be only fs, and as their direction is the same, so what if theta is 0, what I am saying, in whatever direction is the force I am applying, in same direction my displacement is happening, and work is nothing but the energy. They are similar. Same thing is happening here. Now same thing is happening here. If acceleration is along certain axis, and for potential energy difference, we take height along that axis. Until now it was vertical, so we were taking vertical distance. But now potential energy difference, my force, that means my acceleration is along a non-vertical axis. So my displacement will be also along that. My displacement will be also along that non-vertical axis. That's why I will have to calculate my h along this axis. That means my h will be from point A to point B. That means 2r. That means 2r. So this will be g square plus a square into 2r. So equation of u will be 5 into a square plus g square raised to 1 by 2 into r. See, once again, I had written generalized formula for H relation between u square, v square and force balance. There, if you put, what did I say? If you put effective acceleration at the place of g, you will get the answers. That's what we are doing. That's what we are doing. So this was the case where frame of reference was accelerating towards in horizontal direction. Now you can apply this principle with any non-inertial frame of reference. Either it is vertical, either it is excuse me, either it is accelerating upward, downward, horizontally, left, right, or at some angle with x and x or y axis. If you know the concept, this you can solve any examples, any problems on circular motion in non-inertial frame of reference. Now this was the case for this was the special case of circular motion in non-inertial frame of reference. I think we have finished all of the parts in circular motion. We have to do some numericals, don't worry. If there is something missing, I will definitely take it. Don't worry. You won't miss a thing. So, whatever we have learned until now, you can at least start to solve some easy or medium level examples on circular motion. You can even try some hard examples and see where you are lacking, so you will be able to focus on that part and perform good in circular motion. So have a nice day. We will be back in numerical session and our numericals are gonna be very interesting.